we're discussing two theories of acids and bases. When an acid molecule loses its proton, it actually becomes a base, since the ion that results could react with water as a base and turn back into an acid. The acid and base are referred to here as conjugate acid-base pairs. Let's look at this. According to Arrhenius, early 20th century, an acid is a substance that when dissolved in water, it increases the concentration of hydrogen ions. And we know that hydrogen chloride dissolves in water, acetic acid as well, even ammonium chloride, a salt, will increase the concentration of hydrogen ions. A base is a substance that when dissolved in water increases the concentration of hydroxide ions. So the strong base sodium hydroxide, the weak base ammonium hydroxide, and even the salt sodium acetate are bases. The Arrhenius acid-base reaction is quite simple. It's the traditional chemistry 1 acid-base reaction that you studied. Some acid, here symbolized as HA, reacts with some base, here MOH, to form the M plus ion, could be 2 plus, 3 plus, it doesn't matter, plus the negative anion, and water. All reactions then form salts in water. So hydrobromic acid reacts with potassium hydroxide to form potassium and bromide salts and water. An acid reacts with a base to form water and a salt. The problem, however, with this definition is that we know ammonia gas reacts with hydrogen chloride gas both in and out of water. As acids, are they reacting as an acid and base? Arrhenius would say no. But we know ammonia does react with hydrogen chloride. It forms the white smoke you see here, ammonium chloride. So Bronsted-Lowry have a separate theory. It's an advance over the Arrhenius. They define acids as proton donors. So hydrochloric acid, acetic acid, ammonium chloride are still fine as acids. They define bases as proton acceptors. Well, hydroxide does accept a proton, becoming water. But now, ammonia, the gas, is a base because it can accept a proton to become NH4 plus, the ammonium ion. So now we've expanded our definition of bases using Bronsted and Lowry's definition. This is a diagram of what is going on there. You can see the hydrogen ion from water will attach to the ammonia unpaired or lone pair electrons, and that is an acid-base reaction. We now have some new terminology to learn. Now both sides of the acid-base equation have an acid and a base. Seeing here the base on the left and the acid on the right, but here an acid on the left, the ammonium ion, and the hydroxide base on the right. So to distinguish them, we call the reactants the acid and the base, and the products we call the conjugate acid and the conjugate base. As you can see, the conjugate acid is made up mostly of the original base, and the conjugate base comes from the original acid. So let's identify acids and bases. What structural characteristic do acids have? Well, they have to have a proton that you can lose. For instance, hydrogen ions bonded to a low energy anion, like hydrogen chloride, hydrogen hydroxide, and this acetic acid here. The resulting anion must be low energy, must be able to hang on its own. So ammonia gas, even though it has hydrogens, since it would form an NH2 minus ion, which is very high energy. This is not considered to be an acid, and methane is not considered to be acid, because if it lost a hydrogen ion, you'd be left with a CH3 minus ion, which is very high energy. Identifying bases. What structural characteristic do they have? Well, they have to be able to accept a hydrogen ion, so they should have an unbonded electron pair. Ideally, even, it might have a negative charge, like the hydroxide ion. For example, hydroxide, cyanide, phosphate, and we saw ammonia gas, all have either unbonded electron pairs or both unbonded electron pairs and negative charges. Now, are there molecules that can go both ways? Yes. We call these amphoteric compounds, amphotheroi in the Greek. They act as acids or bases, depending on the environment. Take a look at hydrogen hydroxide, water, the polar molecule. It can lose one of its protons, we've already seen that, but since it's got a lone pair here, actually two lone pairs, it can accept a proton to that negative end. So it can go both ways. Other amphoteric compounds, zinc oxide, basic and acidic reactions. Aluminum hydroxide can act as a base, of course, reacting with hydrochloric acid, for instance, or in your stomach, neutralizing the hydrochloric acid there. But it can also act as an acid, and in this case, the hydrogen ions would be attached to the aluminate AlO3 with a negative 3 charge ion. So, you tell us these 5 ions or compounds, are they acids, bases, or both? Turn off the video, solve the equation. You might want to draw Lewis structures to help, and then check your answers. The hydrogen carbonate can either add a proton to become carbonic acid or lose a proton to become the carbonate. It can go both ways. Hydrogen sulfide can lose a proton only to become hydrogen sulfide ion. The ammonium hydroxide can react with hydrogen ions to form water using the hydroxide ion, therefore it is a base. Cyanide ion can react with hydrogen ions to form hydrogen cyanide. It's a base with unbonded electron pairs. And the dihydrogen phosphate can add a proton to become phosphoric acid, H3PO4, or lose a proton to become the the hydrogen phosphate ion, HPO4 2-. Substances that can either gain or lose a proton, we also use the term amphiprotic. Water then is amphiprotic because it can either gain another hydrogen ion or lose a hydrogen ion. This shows water interacting with the hydrogen ion coming out of hydrochloric or hydrobromic acid. Many texts limit this to one water molecule forming the hydronium ion, but that is a construct. The hydrogen ion is surrounded by multiple hydroxide ions in reality. But if we go along with the idea of the hydronium ion, H3O+, we can show the dissolving of a strong acid in water as an acid-base reaction. You can see that diagrammed here as an equation, or here in picture, the hydrogen ion being stolen from the hydrogen chloride. In reality, remember, hydrogen chloride is a very strong acid, and therefore this is, again, simply an imaginative way of looking at it. So you have the acid and the base, and here the conjugate base, which could accept a hydrogen ion, say, from sulfuric acid somewhere, and the acid H3O+. How do you write conjugate bases or acids? Well, note that hydrochloric acid, a strong acid, yields chloride, which is a weak conjugate base. And the weak base, hydrogen hydroxide, once it gained a proton, became H3O+, a strong acid. The chloride ion is a weak base because it really isn't interested in grabbing a hydrogen ion at all. It has to be forced, say by reacting with concentrated sulfuric acid. It must be forced to take hydrogen ions. That's also why HOH is a weak base, because there's so few hydrogen ions. Remember, in a liter of water you've got 10 to the negative 7th molarity, very, very small concentration. So, let's practice. Remember, you turn an acid into a conjugate base by taking away the proton. You turn a base into a conjugate acid by adding a proton. So, for these acids, write the conjugate base. Turn off the video, write your base, and then check your work. There are your answers. Bromide, acetate, and ammonia result from taking a hydrogen ion away. Do the same thing here. Turn the base into a conjugate acid by adding a proton. Turn off the player and then turn it back on when you've solved the problem. And I think that's pretty easy. We've added a hydrogen ion to each of the bases to form the conjugate acid. This is a diagram that has helped some students to understand how an acid becomes a conjugate base by removing the hydrogen ion, and a base becomes a conjugate acid by adding a hydrogen ion. Strong and weak. Strong acids lose hydrogen ions and become weak conjugate bases. Hydrochloric, strong acid becomes the weak chloride ion base. Strong bases, down here, gain hydrogen ions, here's hydroxide, and become weak conjugate acids. So, looking at the table and looking at these formulas, will these species act as a strong or weak acid? Turn off the video and then come back when you've solved the problem and check your answers. These are weak, 1, 2, 3, and 5. The hydronium ion is, of course, a strong acid. Remember, hydroxide is a weak acid because by losing a proton, it would become a very strong base, the O2 2-. Will the base grab protons? Well, look at these bases and answer the question. And that means that these would be strong bases if they grab protons well. Fluoride, hydrogen sulfide ions, and the hydrogen phosphate and the hydroxide. And they are good bases, whereas water will not grab protons well. Another way to look at strength, in an acid-base reaction, the equilibrium adjusts to move the proton to the stronger base. So what's stronger here? The chloride ion or the water? The water is a stronger base, so the hydrogen ion moves from the chloride to the water, and then of course is surrounded by water molecules. You try one. Which reaction will be favored when acetic acid is dissolved in water? There is your reaction, and will this shift to the right or to the left? The acetate is a stronger base than water, so the equilibrium will favor the hydrogen ion from here bonding to the acetate, and not much of the acetate ion will be left. The hydrogen ion concentration will therefore be relatively low. The pH will be higher than that of a strong acid. The equilibrium constant left to right then is quite low.